Computer, what's up?
Hello.
How are you? Did you
I
have a nice
survived.
weekend?
I survived another weekend.
That's nice.
Okay.
I have a quick question about the take-home quiz before class starts.
What's up?
Question two, is it similar to question or example 8 in the notes,
Yeah.
11.1? Okay, because it's worded a little bit differently, so I wasn't sure if I should go about it the same way.
No, your intuition is correct on that aspect. I
Okay, and then I'm unsure of what I should set because when you went over it in the notes in the video, you had it was e to the 0.45 and you made that less than e to the 0.5. How did you get that 0.5 though? Did you just pick the next closest number to it?
so the reason why I got that 0.45
Mhm.
was mainly because I was told in the problem that I want to approximate e to the 0.45.
Oh yeah, yeah, no, I get that, but you can't when you're trying to like approximate it, you can't use that as your maximum value because that's what you're trying to find, correct?
Right. So
Okay,
what
I'm
I
just not
use
sure. Go ahead,
so
you
what
go.
I did do, Anthony, is I used the fact that e to the x is increasing, and I
Hmm.
said, okay, well, 1/2 is definitely bigger than 0.45. And so because of that, I abused the increasing property of e to the x to make that claim.
Okay,
But because 0.15 is just e to the square root,
okay,
that's why I did the step of square root of e. And
okay.
square root of e, well, I know e is 2 point something. So I decided to go a step further to make it easier for computations.
Hmm.
And that's why I did square root of 4 at the end to give me 2 to be
Okay,
my
so
m.
in this case, could I just, since it's e to the 1, could
Hmm.
I say that e to the 1 is less than e squared, and I know that e squared is less than 9?
You could do that. Yeah, that's fine.
Okay,
Yep. But yeah, your idea that is similar. I written it to be similar, so
I figured give a little treat to the kids who actually watch the video.
yeah, bump up my subscriber count on my YouTube channel.
All right, well, thank you.
No, you're welcome. So you need to clarify what problem 2 is asking is finding a bound for the remainder, not to approximate e to the 1. If it was approximate e to the 1, then you would be correct. I would find the fifth order Taylor polynomial and use that. But the goal for problem 2 is to approximate the remainder, which means I'm going to have to use this theorem, which states that for, since it's a Taylor polynomial, remainder is a function, which means I can always bound the Taylor polynomial by the n plus 1 derivative at c, then n plus 1 factorial s minus a to the n plus 1. And then our main goal is to further bound that guy by m. And so that's our main goal for problem 2. So to answer your question, the goal for problem 2 is not to approximate e to the first, is to find the bound for the remainder. Yeah, it's that weird equation with c in it. You're exactly right. Oh no. To make you feel better, Unique, last week I was working on a homework problem for one of my classes, and I spent like a few days working on it, and then I realized that I made one mistake, which made the problem a lot harder, which made me go on a 3-day goose chase. And then because I fixed the one error, I was like, oh, now it's manageable. Okay. So I understand your pain. All right. So with that, I'll go ahead and get started. I want us to spend one more day just doing practice problems for Power Series before we dive into Taylor Series. And the reason why I want to do that, yeah, 11.3 video is up, but y'all learn that Taylor Series are just a very particular form of a Power Series. So my idea is once we get Power Series ironed out, then Taylor Series will be a piece of cake. So we're going to follow our template from last week. I'm going to give y'all problems. Maybe a little bit hard, maybe not. Let's see how y'all do. And so for the first problem, let's see, what's a good one? We've been doing this for a little while. So let's do this to warm ourselves up. And again, it's the same template if you showed up on Friday. I guess for yes case, tell me what the center is for the problem. And state the radius of convergence and the interval of convergence. And let's warm us up with this bad boy. The sum from n equals 1 to infinity of n to the 4nth power s plus 1 to the nth power. Here's going to be a warm-up for the day. I'll give y'all around 10 minutes to work on it. If y'all been doing it for a little while, so let's say we'll, at around 3:45, we'll reconvene and kind of iron out the solutions. Oh, all right, Anthony, if you think you do it in 30 seconds, go to town with it. But let's wait until a quarter till 4 until we get that done. And Isaac, I appreciate the sentiment. And again, just like our regular streams, if you have questions, post them on the chat or unmute your mic and just holler and let me know. See something on the chat. Let me respond to that. Hmm. So I'll address your question, Luke. What a radius of convergence is. Everyone else keep working. I'm just going to address Luke's question during the chat. So for a radius of convergence, the idea is that I want to know when a power series is convergent. Now, unlike with the series we talked about in chapter 10, that one's pretty straightforward with how we determine convergence or divergence. But for a power series, that becomes a little bit more subtle thing to check. And it's mainly because we now have a value x in there that could change based on what we plug in. And so we have to ask ourselves, how can I make sure that I converge based on I could plug in any x? And so for a power series will converge if the distance between any input of x and its center is less than a constant number, positive r. And use positive r is the radius of convergence. And now to find the interval of convergence, you're going to base it off of Yes inequality, because since I have an absolute value of x minus a less than r, I can rewrite that as minus r, x minus a between positive r. And here I'm abusing a fact that if I have an absolute valued quantity that's strictly less than r, I can rewrite it as the quantity inside the absolute value is greater than negative of that positive number, but still less than that positive number. And if I add both sides, all sides of that inequality by the center a, I now have a minus r less than x less than a plus r. And now the advantage of that, because s is in between two numbers essentially, that forms an interval. And so that's how we're going to form a radius of convergence. Or interval of convergence, my bad. I see a message. And I'll respond to that very quickly. Good. People are sending me messages. So with that, I'll give y'all about another minute. And then we'll work on this together. All right. So give me a status report, y'all. How's the problem going? You got some messages from people, but just want a status report at everyone else how they're dealing with the problem. And I'll go ahead and put the problem back up here. Oh, see another message. Respond to that quick. All right. So with that, let's go ahead and walk through the solution. If y'all have any questions while I go through the solution, interrupt me very soon so that way I know what to do. So first off, I saw Isaac's comment that the center is definitely -1. And the reason why to say that is remember that the general form of any power series centered at a number A is the sum going from k0 to infinity. Some constant that is always changing with respect to the index of the series. X minus A raised to the kth power. And so the reason why we have -1 as our center is I see S plus 1, but I can rewrite that as the sum going from 1 to infinity n over 4 of n x minus -1 to the nth power. So that's how I conclude that my center for that series is -1. So with that, let's go ahead and figure out what our power series looks like. So first off, I'm going to say for this guy that I will use the ratio test. Anthony, I like your question, so I'll address it now. So what Anthony is asking is, what if in the general form for a power series, we got something like this going on? And I'll write it down in pink. CFK, and what Anthony is saying is, what if there's a constant in front of that x, which I'll call b, x minus a. And so to find the center of that power series in this scenario, to answer your question, Anthony, I'm going to try to factor that constant out. So what I would do is I would say, all right, I'm going to factor out that constant b, and what's left behind is that x, since I factored out the coefficient b. And because I don't have a coefficient b here, then that means a is now going to be divided by b. Correct. Still being raised to the kth power, which means now I would have coefficient k goes from 0 to infinity, c of k. Because all of this is occurring within that kth power, when I factor it out inside the kth power, I would have b to the kth power times that x to the a over b to the kth power, which would imply, as you mentioned, Anthony, that becomes my center. Glad you asked that, because I think that's a really, really good question. So appreciate that. All right. Now let's get back to our series. So note that even though, how modest. So while I am doing the ratio test, note that you can also do the root test on this guy. It doesn't matter which one you choose. So because of that, I'm going to use ratio, but just note that I could use the root test as well. It's just for this scenario, I decided to use ratio. So let's follow our good practice. Let's write down what my sequence looks like. When I plug in the next term over, let's go ahead and put in for note. Oh, I forgot that n over there with the 4. I can't read today. So 4 to the nth, s plus 1 to the nth power. And so ratio test tells me I'm going to take the limit as n goes to infinity of the ratio a of n plus 1 over a of n, which, instead of one very nasty ratio, I want to take the a of n plus 1 make sure that's in the same fraction, n plus 1. And then I'm going to multiply it by the reciprocal of a of n, which in this scenario will be 4 to the nth power divided by n s plus 1 to the nth power. And now let's try to simplify this guy to make it look pretty and not ugly. I have a 4 to the nth power. I have a 4 to the n plus 1 in the first denominator. So that means I have just 4. Oh, let's make sure I have an n plus 1 there. I have an x plus 1 raised to the nth power. I have an s plus 1 raised to the nth plus 1 power. So that will just simplify down to the x plus 1. And I cannot simplify that n plus 1 and that n because they're not the same expression. So let's clean this up a little bit. That means after canceling, I have the limit as n goes to infinity of x plus 1 to the 4th power times n plus 1 over n. Now, the reason why I decided to separate everyone that has an n with everyone who doesn't is because I'm taking a limit as n goes to infinity. And so because I'm taking that limit as n goes to infinity, that means this part is going to remain inside the limit, while this part, the underlined in purple, is treated as a constant and gets to be factored out. Because they're inside the absolute value, I'm going to use my property of absolute values that says a product within the absolute value is the exact same as taking the absolute value of each number and then multiplying them. So for the first part that I'm going to factor out and take out of the limit, well, 4 is positive, so I'm good there. S plus 1, I don't necessarily know because s could be any number that I choose. So because of that, on my next step, I'm going to keep the absolute value with the x plus 1. But because 4 is already a positive number, having an absolute value will be redundant. Times the limit as n goes to infinity. Absolute value of n plus 1 over n, but because n plus 1 over n, they're always positive because I started with my series at 0, or at 1, my bad. The absolute value is redundant as well. Using our tools from 1060, we could quickly answer that limit equals 1, which means I have the absolute value of x plus 1 over 4. And because I did ratio test, we know that the ratio test converges when that quantity is less than 1. So I'll write that as a reminder. I set this to be less than 1. I'll put in quotation marks because this makes the series convergent via the ratio test. And now I'm very close to that definition of a radius of convergence. X minus the center less than some positive quantity. All I have now is just a 1/4 or a 4 in the denominator. So I multiply both sides by 4 to get rid of that 1/4, which now gives me absolute value of x plus 1 less than 4, or x minus our center, which is -1, is now less than 4. To answer your question, Anthony, my goal with a power series, I want to know what radius and what interval will make the series convergent. So that's how, so I'm not necessarily assuming it's convergent. What I'm trying to figure out is under what interval can I clearly say the power series is convergent. So that's what I'm trying to zero in on. I'm trying to zero in on for what values for x can I boldly say is convergent, which is why I made the step that is less than 1 for that. So so I would be careful with that statement, because when you're saying all intervals convergent, that's not fair. What you're trying to say is, yeah, for what values for x does the series converge? I like the way that Luke answered that, phrased it. That's what I'm trying to zero in. Because if I plug in, say, let's say 4 for x, I'll have 4 plus 1 equals 5. And so by the ratio test, I'll definitely not have a convergent series. And so what I'm trying to do is zero in on what values for x can I boldly say the series converges. And so that's why I'm doing the work. Yep. All right. And now we have a way to zero in because we now have that the radius of convergence is 4. which means starting at -1, I could boldly go 4 distances away, both left and right, to assume that I have convergence. So if I want to draw that out, what that looks like, here's my number line. Let's have 0, and my center is -1. And so what that inequality says is I can go a distance of 4 away from it, which for here will be 3. And for here, it will be -5 if I went 4 away. And what that's now saying is within 4 distance away from that center, I can now boldly say that the series converge. Which implies, based on that photo, that my interval of convergence will be -5 and 3. Let's verify that using math and not with the photo. And so if I had to verify that, say on the final, the way I would do that is x plus 1 less than 4. Using our inequality, that's -4 less than x plus 1 less than 4. And then I subtract everything from 1 to give me what I expected. But I say I'm not done yet. Because I still need to check and see whether or not my endpoints gives me a convergent series or not. And there's only one way that I can think of to do it. Plug into 2 endpoints, see if I have a convergent or a divergent series. So let's start off with x equals 3. Let's plug that into our power series. Let's see if I have a convergent series. So wherever I see an x, I'm now plugging in 3. 3 plus 1, a good day better give me 4. 1 of n over, oh, I chose brown this time, ew. N to the 4n, 4 to the nth power. I see a 4n to the numerator. I see a 4n to the denominator. That goes away. And so I'm now left with the sum as n goes from 1 to infinity of n. And audience participation time. Does that series converge or diverge? Yep. Why? All right, I agree, diverge. Bingo. Diverges by the divergence test. Because if I take the limit of the rule within the series, I get infinity. That definitely ain't 0. So that means by divergence test, that guy is 0, which means I do not include the right endpoint. So that means I have an open interval at 3. So let's now repeat our work at -5. Well, let's see what happens there. Again, sum n equals 1, n over 4n. I plugged in -5, plug in 1 to the nth power. -5 plus 1 on a good day better give me -4. So I have negative 4 to the f power, or I'm going to go ahead and rewrite that as negative 1 to the f power times 4 to the f power. Which what I did was, because I have negative 4 raised by a power, I rewrote it as negative 1 to the f times 4 to the f power. Makes those two go away, which now gives me infinity, n goes from 1 to infinity of n times negative 1 to the f power. And now, again, by audience participation, is this series convergent or divergent? All right. So it's definitely divergent. It's not by alternating series test, because what alternating series test tells me is whether or not the series will converge. It doesn't give me any specifications about if a series diverges. But I agree it diverges. Bingo. And I say we do DNE, I mean by divergence test. Reason why I say that? Limit as n goes to infinity of n times negative 1 to the f power. That is DNE. The reason why it's DNE is because it's oscillating The reason why I know it's oscillating is because of the negative 1 to the nth power. And the limit as n goes to infinity of n is infinity, which does not equal 0. And the reason why I want that detail in there is because if I took the absolute value of that term inside the limit and I get that that goes to 0, that means even though it is oscillating, the limit will still be 0. But because the limit of that positive term is infinity, that means it's just going to get further apart from the x-axis if I draw it out, which is why I conclude that the limit does not exist. All right, so the left endpoint gives me a divergent series, which means I do not include the left endpoint in there as well. Therefore, what that tells me is my interval of convergence for this guy is -5 to 3, open interval for both of them. All right. So how about that for a warm-up? Again, if you have a question about that problem, post it on the chat or unmute your mic and just let me know. And with that, I'll go ahead and start writing up the next problem. It's going to be a repeat of the last time, but now the series I want you to try that on is the following. Let's change my index to k. -1 to the kth power, x to the 2k plus 1 over 2k plus 1 factorial. And so again, it's going to be a repeat. Find the center of that power series. Find the radius of convergence, or what values for x will make the series converge. And then also find the interval of convergence. and I'll give y'all about 6 or 7 minutes to work on it. If y'all have questions, let me know via the chat. I saw a message that I'll respond to. With that, have fun with it. All right. Give me a progress report. How's this problem going? Oh, uh, Anthony, I saw your comment. Yes, I am the one grading it. Um, so the reason why it's slow is because I am slowly catching up. So yeah, I'm the one who's grading to take on quizzes now. I'll give y'all about 3 more minutes on the problem before I go over it. I will be right back. I'm gonna grab myself, refill my water bottle. All right. Give me a status report, y'all. How's this problem going? All right. Isaac is just keep swimming until he got the answer. How about everyone else? How are y'all doing? How's everyone else doing on this problem? Only got a status report from Isaac. All right. Matthew, 75% done. Oh no. Sorry to hear that, Unique. All right. So let's go over the solution. Unique, the short answer to your question is I actually would use the ratio test mainly because I see a factorial popping in. And with a ratio test, it quickly gives me a very cheap and quick way to simplify that problem. Let's go over the solution. First thing, what's the center of my power series? What value did y'all get for the center of that? Well, let's recall a general form. Our general form is always the sum goes to 0, a coefficient x minus the center raised to the kth power. And the thing to note with that kth power, doesn't matter what form that's going to be. And Luke, I agree. It should be 0. Because I can, like I said, it doesn't matter what this exponent looks like. As long as it's x minus a raised by something evaluated at k, I still got it. And so to more express the x to the 2k plus 1, I could rewrite that as x minus 0 to the 2k plus 1 power. So the center of my power series would be 0. So with that, let's go ahead and figure out what makes this bad boy convergent. Nope, don't worry about it, Isaac. That's the point of learning. So I recommend doing ratio tests here. Reason why is, as I noted in when you choose a test for convergent, Anthony, your comment made me laugh. It's because since I saw a factorial, I'm going to use ratio test to essentially get rid of the factorial stuff in there. So let's follow our noses. Let's copy down the kth term, which is -1 to the kth power, x to the 2k plus 1 power, divided by 2k plus 1 factorial. Now let's write down the k plus 1 term of that, which all that just means is -1. And instead of a k, I replace all of that with k plus 1. So x to k plus 1 plus 1 divided by 2 times k plus 1 plus 1 factorial. So let's simplify that a of k plus 1 term, because right now I don't like the fact that I have 2 times a k plus 1 plus another 1. So let's go ahead and make that look nicer. So because I see that 2, I can factor it to that k plus 1, factor it here as well. So I'll get 2k plus 2. And then with that extra plus 1, I'll get 2k plus 3. So -1 to the k plus 1 power x. And now my exponent is simplified down to 2k plus 3. Divided by another 2k plus 3 factorial. And before we do the step of finding our limit, let's go a little bit further with our rewriting. Because I eventually do need to cancel out those factorials. So let's go ahead and rewrite the 2k plus 3 factorial so it becomes a lot easier to simplify and to cancel out once we dealt with that. So definition of a factorial means starting with the base of that factorial, I'm taking the product of that base times, I constantly subtract 1 from it until I get to the number 1. But for the 2k plus 3 factorial, I can always rewrite that as 2k plus 3 times, subtract 1 from it, 3 minus 1 gives me 2, 2k plus 2, times 2k plus 1 times 2k minus 1, which I could just group together as 2k plus 1 factorial. And I want to rewrite that in that form because when I do my step for the ratio test, it's going to make our work a whole lot easier. So let's not do that bad boy. Have L equal to the limit as k goes to infinity of a of k plus 1 over a of k, which equals 2 limit as k goes to infinity of, now my k plus 1 term, after simplifying it, I have negative 1 to the k plus 1 times x to the 2k plus 3 times 2k plus 3 factorial, which I've rewritten as 2k plus 3 times 2k plus 2 times 2k plus 1 factorial, and then the reciprocal of my a of k term, which is the 2 of k plus 1 factorial times the negative 1 to the k power x to the 2k plus 1 factorial, or 2k plus 1 power. Now, one subtlety that I'm going to do to make the simplification a little bit clear is I'm going to go ahead and rewrite s to the 2k plus 3 power, mainly because I could rewrite 3 as 1 plus 2. So I'm going to make a note that I want to rewrite s to the 2k plus 3 as s to the 2k plus 1 times x squared, just to make it clear what's going to be left behind once I do that cancellation. All right, so now we're going to see a lot of stuff dying. First thing that's going to die is the negative 1 to the kth power, and I'm now just left with a negative 1, which that's going to be gone because of the absolute value. 2k plus 1 factorial gets to die off. And I'm now just left with the 2k plus 3 times the 2k plus 2 in the denominator. And the s raised to the 2k plus 1 dies off, leaving me with only x squared. Which means now what I have in my limit, after cleaning up a little bit, is a negative 1 times a x squared times everything else to have k with it. So 1 over 2k plus 3 times 2k plus 2 in the denominator. I'm going to use my property again that says I'm going to take the product and rewrite it as the absolute value of a product as the product of the absolute values. And because that is a constant with respect to k, that's popping outside. So I now have absolute value of x squared times the limit as k goes to infinity of Since k was always positive, since those are my indexes of my series, absolute value is redundant. So 2k plus 3, 2k plus 2 in the denominator. And if I want to compute that limit, what am I going to get at the end? If I evaluated that limit, bingo. Because I have nothing going on in the denominator, in the numerator, and my denominator is getting larger as k goes to infinity, which makes the whole rational function go to 0. Which means my L is 0. And I don't recall from way back in the day, that's definitely less than 1. And so with a power series for radius and interval convergence, let's now dissect what that means, because I don't think with any of our practice problems that we've done something like this. So let's dissect that real quick. So here I concluded that my L for the ratio test will be equal to 0 no matter what value of x I plug in. So typically what we had before was we had an absolute value of x or something, and we used that to form our radius and interval of convergence. But here I don't have an interval that I could absolute value for x that I could form anymore. Oop. I now just have 0, which will always be less than 1. And so what that means is this series is always convergent regardless of the value for x. That is what this work is telling me, is that no matter what value for x I plug in, I will always get a convergent series. No ifs, ands, or buts. And I could be stronger than that because I did the ratio test. I could be stronger and say I always have an absolutely convergent series. Because if I converge by the ratio test, that tells me I'm absolutely convergent. And so because what this work is telling me is that the series will always be absolutely convergent no matter what the value for x will be, what do y'all think my radius of convergence will be for that problem? Or a better way to phrase it, is there a cap where I can go? Bingo. And I agree with you, Luke, Anthony, Isaac. Because my power series will always converge regardless of the value for x that I plug in, that means my radius of convergence is infinity. Upside down infinity. Nice. And what that also tells me is that the interval of convergence, well, if my radius of convergence is infinity, unique, I agree with you full-heartedly. That means my interval of convergence is negative infinity to infinity, which essentially tells us what I wrote in green, that all values for x will still make the series convergent. And so that's what our work is to tell me. So this is the first time we've encountered a power series in these practice problems where, oh, it doesn't matter what I plug in. I'm guaranteed a convergent series. And that's pretty neat. So with that, I'll go ahead and make a note for this problem and for that particular series, which relates to sections 11.3 and 11.4 about Taylor series. Is that yes, that series that y'all worked on, it is the Taylor series of sine of x centered at 0. So y'all encountered one of your very first Taylor series is that this is now a Taylor series that we tackled, which, to kind of tell you what a Taylor series is, if y'all haven't watched the 11.3 video, it's essentially telling me that I can rewrite a function that we talked about as a power series. And so don't be surprised in 11.3 notes to see that as the power series representation for that. And Anthony, yep. And I say Maclaurin series and Taylor series are essentially the same because all the Maclaurin series is that's just a fancy name for a Taylor series centered at 0. That's all Maclaurin series are. They're just a fancy name for a Taylor series if I centered it at 0. So if I wanted to, because when I write, I pay by the letter, I could rewrite Taylor series of sine of x at center at 0 as that is the Maclaurin series at Maclaurin series of sine of x. So fun trivia fact, Anthony. You're not far off. So the reason why we have called Maclaurin series is so Taylor was one of the first guys to ever make these series to represent functions as polynomials, essentially. And Maclaurin, he wrote one of the first calculus books, and he was essentially fascinated by it centered at 0 because it's just a very nice Taylor series when your center is 0. And so because of that, mathematicians later on were like, we'll call a Taylor series center at 0 Maclaurin because this duo is obsessed with them. So you're not far off. Because Maclaurin made his like calculus textbook like 30 years after Taylor first published his work on Taylor series. So you saying Maclaurin series writing off the work of Taylor, I mean, you're not far off. And fun fact about Taylor series, and this just tells you how nerdy I am. So a couple other mathematicians figured out about Taylor series before Taylor. One is Isaac Newton. Like he knew a lot about Taylor series way before Taylor published his work on Taylor series. And the reason why we call it Taylor series was Taylor was the first mathematician to actually publish the work. Isaac Newton, he kind of just had it like just in his storage for notes because he thought it was cool. Well, Newton never published his work. He just used it for whatever. Yeah, and to give Taylor credit, he didn't realize that Newton came up with it before him. So that's why we still give Taylor the credit, because he developed it on his own. So yeah, fun trivia fact from the 1700s. I think, yeah, Taylor is from England, so he was an English mathematician at the time. And I think Maclaurin was a Scottish mathematician. I could be off. He was either English or Scottish. I don't remember 100%. And I can fact check that, but I'll work on the next sample. And that's perfectly fine. So with that, I'll go ahead and answer Unique's question. So take home quiz 10, problem 5. And so the reason why I gave y'all the hint to check the relation with 5, and so since I'm addressing problem 5, I'm also going to address problem 6, because I gave y'all the same hint. And bingo, that's exactly an infinite. So I'm going to recall 2 properties that we have from section 11.2. Is that if I have a power series, and I'll go ahead and write this in the general form. The first property tells me that if I take the derivative of a power series, then we should do as we expect, which means I can move that derivative inside the power series and take the derivative term by term. And do it that way. And now, by the power rule, no matter what value I take, I'm always going to do power rule, because x is underlying in here. And so that means our formula for derivative of a power series, C of k is a constant, so that's not affected. Taking derivative will give me k times x minus a to the k minus 1. But because I'm taking derivative of a power series, I'm actually going to start off at 1. The reason why I'm starting off at 1 is because if I plug in 0 to my original power series, I'll just have C of k. And because that coefficient is a constant with respect to x, I get 0. Thus, I start off my new power series at 1 and not at 0. And also for a power series, if I take its integral of a power series, I should expect essentially the exact same thing that I've done in part 1. Which means integral gets to move in. which means I now have the sum from k equals 0 of c of k. Because I'm taking antiderivative of x minus a to the kth power, it's now going to be k plus 1 divided by another k plus 1. And then I'm going to have a plus c. And keep in mind that that plus c is on the outside of that series, mainly because I'm integrating the entire power series. So just keep that in mind to avoid confusion.
Can you say that these are then equal to the sum in the original problem this form? I'm just confused with the relation between these.
So not necessarily equal to the sum of the original form. So the reason why I'm doing, so the way I can relate them is, let's start with 5. Actually, before I go on, when you mean relationship, Anthony, are you talking about how do I relate the derivative to the original power series?
Yeah, like basically, like how do you set it up to like get it into a form that you can then do everything to?
Got you. So let's do that
Because
with
like
5.
this is just these properties make sense, but it's like how do they relate back to the original problem?
Got you. So let's do that with 5, and let's see if we can answer it that way. So, like you note, Anthony, one g of x, part of it, I have the derivative popping up, but it's not just the x, it's just the 2 minus x, all of that squared. So what I would do in this case is I would rewrite it as s squared times 1 over 2 minus x squared, which is equal to 1 over 2 minus x squared. And this portion is the derivative of 2 minus x. Now, that's not a form that I'm used to seeing. So what I need to do is transform it into a power series representation that I know. And the way that I can do that is I need to transform it into the 1 over 1 minus x. And because I have that coefficient of 2, I need to factor that 2 out to give me 1/2 times the sum k equals to 0 to infinity of x over 2 to the kth power. And then to converge,
Wouldn't you need to keep the x of m in too? So you need to put the x squared on the outside
you're talking about that x squared?
in the purple.
That's going to come later. I'm just writing down the power series for 1 over 2 minus x, not the power series for g of x.
Okay, but when you do g of x, you need to then do that x of m property.
Correct. I do need that for later.
Okay.
So you're exactly right. And then what you mentioned, Anthony, that's what I'm going to do. I'm going to take derivative of this power series that I just have to give me my brand new series. And then at the very end, then I use the property that you were mentioned before, which tells me that s squared gets to move inside.
Would you use the derivative property or the integral property? Just because it is the derivative, so
that means that means I have to use property 1.
Okay.
Which means that I need to take the derivative of this guy, which means I'll take derivative term by term. So that means I could rewrite this as the sum, or 1/2 times the sum, k equals 0 to infinity, of d of dx of x over 2 to the kth power. So that's me now using property 1 above.
Okay.
And the reason why I want to do that is now I'm taking derivatives term by term, and I can use power rule now.
And for number 6, with the natural log, you just kind of like then just use the natural log and do the same thing, but just put the natural log there.
Bingo. So, right. So for the relationship with h of x with the natural log of 2 minus x is if I take the integral of 2 minus x dx, I get negative natural log of 2 minus x. And then because we'll take points off, it'll work. We have that.
Why is it negative natural log?
Because if I do a u sub, my u will be 2 minus x, which makes my du negative 1.
Okay, that makes sense. Yeah.
Yep. And so that means to get h of x, I'll have a negative sign up in front. And then just like before, Anthony, I would then use property 2 again and take the integral term by term of my known power series. Oh, Luke, I see your question. So the thing about derivative of a power series is they have a powerful property in which I get to keep the radius of convergence, but I don't necessarily get to keep the interval of convergence. And what I mean is, so I'll go ahead and write down the radius of convergence and the interval for convergence for that original series. The radius of convergence is preserved with my derivative and the integral of my power series, but there are cases where as soon as I take the derivative, I could perhaps include the endpoints now in my interval of convergence. Or vice versa, let's say after I did all my work, let's say I included the point -2. While that worked for the original power series, once I take its derivative, plug in -2, I actually showed that I don't get it anymore. And so that's what it means, is that for a derivative, I actually get to include my original radius of convergence, but I have to be more careful about the interval of convergence. So I have to recheck that. Right, I keep the radius, but I might actually change my interval of convergence based on my new power series. Anthony, going back to you, does that answer your question with sets? Because that's how we're going to tackle it for sets.
Yeah, that makes sense.
Okay.
Thank you.
No, you're welcome. How do you find my brand new center? So another thing, Luke, your center is also preserved with taking the derivative and the integral, because you look at my two properties, the center is not changing. I still have an x minus a raised by some power that's dependent on my index k. And that's true for both the derivative and for an integral of a power series. So that's another powerful concept with our derivative and integral of a power series, is the center is preserved and the radius is preserved. The way that the interval changed, Luke, is if I plug in the endpoints, there could be a case where I have, say, a brand new, I include one of my endpoints. That's what I mean. So let's go through the sample on 11.2. Let's see if I can find a good one that I wrote. So that's all that's going to be changing, Luke, is our endpoints essentially. And so here's one example where my interval convergence did change. Example 8 here. So first I used the power series, right? So I have to check that again. And in this example, my original radius of convergence was -1 to 1 with the left endpoint included. But when I plugged in -1 into my brand new power series, I actually showed that it can diverge by limit comparison test, which means that I altered my interval of convergence. Not a very slight change, but it's still a significant change that we need to double check and make sure. So I should have clarified that with you, Luke, that only the endpoints will be really changing. Yep. All right. So let's see. I forgot which page we were on. So, any other questions that y'all want to work on? I was getting close near the end, but if y'all have any last minute questions for everyone who's here, go ahead and answer them. If not, then if y'all want to stay for a little bit, we can go through one more problem with the power series. It's going to be your call. All right. See you tomorrow, Anthony. Go ahead, Luke. So the hardest part with the remainder is the remainder sucks. That's going to be the best way that I'm going to say. And it's the reason why is because the remainder formula for and I'm going to talk about a power series, Luke, because a Taylor series is a power series with a very specific coefficient. And so for yes, I'll just go ahead and mention a power series to be more broad. A remainder for a power series is the nth plus 1 power at c, n plus 1 factorial x minus the center to the n plus 1, where c is between x and a. And this is very nasty. I'm not going to lie to you. That is a very nasty exact formula for a remainder. Now, the reason why we have C between x and a is because if you want to go through the groundwork and actually prove this guy, the proof is essentially mean value theorem, but we reworked in essence to work with the nth plus 1 derivative. But to find the exact remainder for a power series, that actually becomes very hard, mainly because what is C? it's just any point in between x and a, so I can't really give a specific case. Because of that, the best thing I can do is estimate the remainder of a power series. Right, C is just some point in between the interval x and the center A. So C is just an arbitrary point in between. Yeah, you could think of it like that, where I can't really figure out what it is, so we're trying to estimate it the best we can. And the way that we're going to estimate is we want to take the absolute value of the remainder, which is the exact same thing as the error. So because I'm taking a product of everything inside the absolute value, product inside absolute value is the same as absolute value of every part of the product. So I'm going to rewrite that as f to the n plus 1 c absolute value of x plus h to the n plus 1 . And then because n plus 1 factorial is already a positive number, absolute value of a positive number is redundant. What is n? So n is referring to, with, say, my power series, how many terms do I want to replace it? So you can think of it as, back in chapter 10, when we talked about the remainder, say, for the integral test and for alternating series. Yeah, it's how many terms am I adding into my partial sum? Right. And so the way that we're estimating the remainder is I do need this particular fact that quantity f to the f plus 1 derivative of f evaluated at c, I want that quantity to be less than or equal to m which is some positive number. And so essentially what our goal is for estimating the remainder is, if I showed that this quantity is bounded above by some positive number m, then I could say I can estimate my remainder with that multiply m times x minus the center n plus 1 divided by n plus 1 factorial. And so this guy is what's boxed in there. I do not think Dr. Burr is going to give that to you. Oh, are you talking about the estimate, or are you talking about the actual remainder equation up here? Okay. I would actually prefer to remember how to estimate it. And the reason why is because this is technical as is, and it'll get nasty if, say, like, let's say, for example, I want you to approximate it with 10 values. So n equals 10. Then by that equation, I'm taking the 11th derivative, and that's already going to be nasty. So I would be more inclined to just remember how to estimate the remainder of a power series. Yep. And one thing to note, you can cheat a little bit by using tools that we had before. And what I mean by cheating, since we talked about this today, I'll now go ahead and use this. K s to the 2k plus 1 over 2k plus 1 factorial. And one of the examples we did today, I gave you all yet as a problem, and I already let y'all know that that's the Maclaurin series. But let's say I want to approximate it with the, let's make it just god awful. Let's say the 21st Taylor polynomial, which means n will be 21. Even though sine, when you take its derivative, will circle back and forth every fourth derivative, I still don't want to do that because that's just tedious work. And so when I calculate the 21st remainder of x, well, by our equation, that means I'm going to have to take the 22nd derivative, 22nd factorial, times, and because it's the Maclaurin series, x to the 22nd power equal to f 22nd c times absolute value of x to the 22nd power divided by 22 factorial. And the reason why I say you can cheat a little bit is because whenever I'm taking derivatives of sine or cosine, I'm just bouncing back and forth between sine and cosine. And so I don't care how many derivatives I'm taking, I'm either going to get a sine or a cosine, which means this will always be bounded by 1 because my outputs for sine and cosine are always between -1 and 1. Which in turn means n will just equal 1. And so I use that to help me cheat a little bit. I think that kind of helps. Does that kind of help out, Luke, in that sense? Okay. Yeah, and that's sort of some of the nice part about when you estimate the remainder is that, yeah, it sucks and it's annoying, but we can kind of cheat a little bit with stuff like that, using some of our knowledge back in our toolkits from before. And then as for x, that value will typically be given to you either explicitly or implicitly. So another example where it's given implicitly, one of the examples in the lecture notes for 11.1 was I gave e to the 0.45. This is a case where I gave you the value for s implicitly. Because I gave you the function and I also gave you the input that I want you to particularly approximate with. So that could be fair game on, say, the final or on your MATLAB math. Is that the value for x could be given to you implicitly and not explicitly. Right, and that's what you're going to do next, Unique. Remember that derivative of a power series, it preserves the radius of convergence. What will be different now will be the endpoints for my interval of convergence. So you're going to use the x over 2 to find the radius of convergence, because taking derivative or a integral of a power series preserves the radius of convergence and the center. So the main reason why we talked about derivative of a power series, in that sense, is to make our work a lot easier. So one case is, yeah, we could take derivative of nasty functions like, oh, I don't know, 1 over 1 minus x. And while that's valid, that's not too bad of a derivative now. We could go around that nasty work by using this power series, taking the derivative term by term, and we now have a slick way of calculating its derivative for that. So that's why people talked about it that case. Is that with power series, we can still do our basic operations of integral and divergence. And when we talk about Taylor series, it's going to help out a lot more, because now when we talk about more about Taylor series, instead of doing nasty integrals or nasty derivatives, I could just be like, oh, use the Taylor series, take derivative term by term. I now have the derivative. So essentially, it's a tool-saving kit of why we do derivative and integrals of a power series. So that's why we officially take it. And it's also to help us save a whole lot of tedious work. So for example, in problem 5, if I did not recognize that it was the derivative of 1 over 2 minus x, then finding the power series representation becomes a whole lot more work, and a whole lot more work that I don't want to do. Now, didn't I kind of answer your question, Unique? That makes sense? All right. All right. So I kept y'all 15 minutes over. Any last minute questions? All right. In that case, I will conclude our Zoom meeting, which from what I consider Zoom to be a wannabe Twitch stream. So with that, I'll see y'all tomorrow. And if y'all have any questions, keep in mind I'll keep my email open. So if y'all have further questions about Take 'Em Quiz 10 while y'all are completing it, shoot me an email and I'll try to answer ASAP. All right. See y'all.